So this is the handouts, and as you can see, the preliminary schedule. So 3 to 3:30 here. Let me make this bigger. So this is our preliminary schedule, 3 to 3:30. I'll be talking about the SAVI monitoring architecture, which we named Monarch because, well, lack of creativity. And then 3:30 to 4, we'll talk about the transition that's currently going on in the SAVI testbed right now to support IoT services and IoT virtualization. And then in the last hour, we'll do a little bit of hands-on related to containers in IoT platform management. So I think right now, yeah, we're about 20 minutes behind, but it shouldn't take long because there weren't. So I'll start with the Monarch, the monitoring architecture of SAVI. Okay, that's not working. Slideshow, use that, okay. Okay, cool. So Monarch is an integrated multi-layer monitoring system that was developed by a previous master students on our testbed. It's primarily an architecture, so what that means is that the actual components that goes into realizing this architecture can be easily swapped in and out. So basically, for the monitoring and analytics, anyone who's ever ever managed more like a group of computers at all, sort of. So oftentimes, like as you scale, you eventually realize that you need a monitoring system to actually proactively monitor and alert you when things are not working. And especially when you're running something like the SAVI testbed, which is essentially a platform for other users, you also have to be aware of what those other users are using your testbed for. For example, you don't want them to be using virtual machines as a botnet, as an example. And you also don't want your virtual machines, like your own infrastructure to be compromised. I can tell you right now that like almost every week we get attempts by outside, we don't know who, trying to break into our infrastructure. We've spent a lot of time trying to secure our system against that. A lot of times the IPs, the attacks come from botnets based somewhere in India or China or Vietnam. That's usually where they come from. So Monarch, so the SAVI monitoring architecture, it's an integrated monitoring platform, and it's used to assess the state of our entire infrastructure. And so what are the challenges when you want to make a monitoring system for a cloud, basically? First, it has to be scalable because the size of the cloud, and a single physical machine can easily host up to 20 to 40 virtual machines, right? So you need to be able to monitor those 40 virtual machines times the number of physical machines that you have. So it grows really fast. Second is that it should be able to support both structured and unstructured data. For those of you who have worked with databases, you'll probably know that NoSQL has become a very famous, well not famous, but like it's becoming a trend to use NoSQL databases. What this means is that the database is not directly relational. And the ability to store unstructured data with no defined schema is extremely important because as you're moving towards an IoT infrastructure, you don't know what the sources are going to be, right? So if you integrate a new sensor, you don't necessarily know how that sensor is going to represent its data in the network. Is it going to be JSON? Is it going to be XML? Is it going to be something that they invent themselves? Regardless, you should be able to take whatever data format they have and store it, right? So unstructured data. Multiple layers, again, because this is a cloud, we have physical layer and then we have virtual layer, right? And this isn't only for compute, it's also for the network. We have the physical network, but again, that physical network is shared by many different tenants, many different projects. As you guys probably have experienced this morning, you're all sharing the same physical infrastructure, but you're all just isolated from one another. And again, like there can be a number of complex behaviors in the system that we can't account for. So basically, the monitoring system here is a multi-layer monitoring system, as I mentioned, and we strived to use open source tools as much as possible, right? So when we collect data, we do two things with it. One, we may want to do live analytics on it so that we can react as soon as possible whenever we detect some sort of anomaly or whatever. Second is that we want to be able to store the data as well, to do analysis later on if we need to. Or if we, for example, if we discover a new anomalous signature, we want to be able to look through our historical history to see, okay, when did this begin, right? And you can with storage, you can also get into things like trending, like historical trending, so you learn when resources are being used, when they're not being used, et cetera, et cetera. So yeah, so in SAVI, because SAVI leverages OpenStack, which in this morning I explained is the open source cloud management software suite. OpenStack includes a tool called Ceilometer, which collects some data, but we don't only want to collect the data that Ceilometer offers, which is mostly information regarding your virtual machines. We also want to collect information regarding the network as well, and that's where we collect data using OpenFlow. So we're collecting data on virtual machines and the network. So this is a high-level overview of the Monarch architecture. So it's a multi-layer architecture. On the very left, this is the acquisition layer. So every physical machine we have local agent processes. These agent local processes are closest to the resource, so they can continuously monitor the resource utilization, see if the state is on or off, etc. So this data is continuously being streamed through a messaging system, and it can be any messaging system you want. It can be RabbitMQ, Kafka, etc. For those of you who have worked with these kind of technologies. So this transportation layer, so the data is streamed into essentially storage for, as I mentioned earlier, you want to be able to store this data, while at the same time it's also being put into a stream processing system, like for example Apache Spark, if any of you have worked with that. So there's some analytics going on in the stream processing system, and depending on different alarms that the user can set up and different dashboards, you can visualize the current health of the infrastructure, and you can also have notification systems to say, hey, something weird was detected, etc. And again, to allow users to develop their own more complicated dashboards, we also expose a set of APIs for users to develop their own analytics on top. So there's a video which I will show. It's about 2 minutes, I believe, and it's basically a demo of the Monarch, the current implemented Monarch system on the SAVI testbed. Let me just get this video up and running. So yeah, it's exactly 2 minutes. Let me put it here. Okay, everyone can see this? Good. Oh, wait a minute. Audio. I need audio. Okay, I guess I will crank my speaker up as high as possible.
In this demo, we'll present Monarch monitoring capabilities of creating cross-layer resource graph and how we can use that for anomaly detection. First, log in as admin and click onto the resource graph, and this graph shows connectivity and relationship of resource in data center.
So really quick point, in SAVI for collecting all our information, we like to leverage graph databases, because as you scale, essentially what you want to be able to analyze is the relations between different resources, right? Which machines are talking to which machines, who's talking to who, and how much. So you want to be able to not only visualize resource utilization, like for example, like we use colors to represent the current level of resource utilization of physical machines, virtual machines, physical network, virtual network, storage, etc. Disk read and writes, that's also important. But we also want to be able to visualize the relationship between different nodes. So everything is a graph.
The black border node represents the VM that the user has. The yellow border node represents the physical machine that the VM is in. The links between are OpenFlow based. We create this graph by processing OpenFlow monitoring data as well as other monitoring data. You can see that there are some difference in the color inside the node. The darker the color of the node is, the less CPU it uses. In contrast, the more red the color of the node is, the higher CPU usage it has. Another feature is that the smaller the size of the node is, the smaller its flavor is. Move on to a yellow border node. We can view the name of the physical machine. Move around to the black border node. We can see the VM name, username, project name, and flavor. By checking on the VM communication, we can see the VM's communication which are represented by a link between VM to another VM. Now we uncheck the physical machine button. Physical machine and its connection to VM are removed from the graph. Now the graph only shows the VM and VM communication. By checking the filter isolated VM, we can obtain a graph of VM that has at least one communication to another VM. To view anomalies, go to Anomalies tab. User will be able to view the anomalies detected with message displayed. Then we can click on the ID to view the structured VM and VM communication before and after the anomaly detection. This detailed page shows the comparison before and after the detection. Log in as a user and click on the resource graph. The user can only view his own VM. With the same process by clicking VM communication button above, we can see the VM communication. By unchecking the physical machine button, the physical machine and its link to other VM are removed from the graph. Then we check on the filter isolated VM. We can see that there's only one group of VMs that are communicating with each other in this user's account.
So I know that was a little bit fast, but any questions so far, or should I, yeah?
Are you using something like Network X to visualize those graphs?
That is all D3. It's a front end, but in the back end, Spark, we use Apache Spark to analyze the data. So it's continuously monitoring like which VMs are talking with who, and basically every 5 or 10 minutes, I forgot, it dumps a new JSON file, which is used, and D3 reads from this JSON file to plot this. D3 is just a JavaScript library, right? So I'll go back let me turn off the volume and then I just wanted to point some things out that because I realized it was super fast. So in this view right here, so first of all, this guy, at this point, he's logged into the admin network, so he can see everything, what everyone is doing. So these big red ones in the center, these are physical machines. And as you can see, their CPU utilization is pretty high right now. And these smaller ones on the side, these are virtual machines that exist on top of this physical machine. And then again, from the color, you can tell, is this virtual machine using a lot of CPU or not, etc. So then he went forward and then he clicked on VM communication, so you can visualize which VMs are communicating with who. And then you get this mess. And yeah. And it kind of spreads out a little bit, right? And then later on, he clicks on the very right, he clicks on filter isolated VMs, because some VMs may not be used to communicate with other VMs. But sometimes you may have a group of VMs that are talking with each other, like here or here. This is interesting right here. From the pattern, you can probably infer that, for example, this node right here could be a load balancer, for example, load balancing between a bunch of different other VMs. Whereas something more like heavily connected like this could be some sort of, for example, like a distributed database that has to continuously sync with one another. So being able to recognize patterns and graphs is extremely useful in this context. And yeah, any other questions? Go ahead.
And how do you use it? Can you click into the docs and see what exact virtual machine is?
Yeah, he went through it super fast. At one point, you can hover over it and then you can see the virtual machine's UUID. So it's small, sorry. You can see the name of the virtual machine, the unique ID of the virtual machine. You can see what tenant it is, and you can see what like flavor it is. So you can get that data. Yeah.
What is the best way to see how much practical communication happens in between the VMs?
Sorry, can you repeat that?
What is the practical way to measure VM communications? And
What's the practical way? Or
before is checking if they are connected or not.
currently, as far as I understand, so like I said, this isn't exactly my work. Currently, as I understand, under the hood, it's collecting all the data via overflow. So it's checking the flow tables and stuff like that. So it can know who's like so basically, because our entire infrastructure is run using SDN. And again, as Liang Garcia briefly pointed out this morning, we don't allow any broadcast types of traffic, like for example ARPs or whatever. We never allow any broadcasts. So all the networking in our entire testbed has to be set up by basically an SDN system, right? So basically, if you're a VM that's talking with another VM, that has to be explicitly allowed. So we're always in a state of tracking which VMs are talking with who. Because, like I said, when you control the entire network programmatically, you have the ability to save this like state in a database and then just analyze that. And that can be used to create these graphs. Any other questions? Cool. So this is like, this is essentially what Liang Garcia was talking about this morning, that in the sense that we're not only doing software-defined networking, we're doing software-defined infrastructure. Everything is controlled and managed via software tools. So we can track network utilization, disk utilization, CPU utilization, memory, etc. So that basically is a quick key of Monarch. There was a Monarch tutorial, but for the purposes of time, we scrapped it. Right, so if there's no questions, I'll move on to another quick presentation related to, let me close this, related to IoT. So in the last year and a half, in SAVI, we've started trying to transition the testbed into supporting IoT-related services and devices. So as Liang Garcia talked about this morning, SAVI traditionally has two tiers. One is the core data center tier, which is large-scale traditional data centers that hosts hundreds of CPU cores. And then we have smaller data centers at the edge, closer to the end users. But as you move into IoT-related stuff, you've seen that people you can buy like cheap Raspberry Pis, cheap sensors. At U of T, there's a store close by called Creatron. You walk in, you can buy these small sensors that are $2 or $3 each. And then if you have the soldering skills, you can even create your own unique sensors and stuff. It's kind of fun if you like small-scale electronics. And so these small sensors are usually deployed in, for example, your own home, in a room, etc., to monitor a wide variety of environmental variables. And if you want to do some sort of control system, it's not just sensors, it's also actuators, right? And so you need some sort of control loop. So usually these control loop software, they're usually running in like very tiny edge devices like Raspberry Pis, Arduinos, or Onions. And these things are usually existing on-premise where a user is. We couldn't bring one, but that would have been cool to bring one. But I'll show you really quickly. So we have a postdoc that in SAVI right now who's working on how to transition the testbed to support these kind of services, because we want to extend the virtualization beyond the edge data center and into the actual home of the user. So I'll briefly go through this, which is presented from his, he wrote a paper and he presented this earlier this month. I got permission to present this really fast. So SAVI IoT, end-to-end management of IoT applications. So just as a quickie review, and I remember on Monday, the lecturer then talked about how a lot of IoT architectures now have a new layer, aggregator layer, and then the things. So I'll really quickly go through it right now, because I don't think she went into any detail. But this is basically all the layers to any IoT application stack. You have the things and devices, sensors, firmware or actuators or anything here. So these are the small devices that you have. Traditionally, these things have to be interconnected somehow, and they're usually connected to something local. Like I said, like a Raspberry Pi or an Arduino. These can be used as basically the aggregation layer to collect the data, aggregate the data, and maybe do some pre-processing on them. And then these two layers are basically the same as what SAVI has been pitching, which is the edge data center layer and the core data center layer. And then on top is like the application, right? In terms of how it's visually represented to the user and how users can interact back with it. So these are things like portals, dashboards, mobile apps, and etc. So this is a layered architecture, a very high level layered architecture of how we think IoT should be developed in a cloud kind of sense. Again, if anyone wants to ask me any questions, just feel free to interrupt. So lessons from cloud computing, and again, this was briefly covered by the lecturer yesterday. So traditional cloud computing is all based on hypervisor-based virtualization, so virtual machines. But in recent years, in the recent 2-3 years, containers, has anyone heard of containers or have played around with containers? You too? Okay, so in recent years, containers have become much more accessible, and so containers have been around for a long, long time. Google has been using containers since early to mid 2000s, but it wasn't until I think 2013 or so that companies have created tools to make it easier for regular users to create containers, that it's really taken off as a lightweight alternative to virtual machines. So I'm not going to go into details of under the hood how containers are realized, but basically, so Docker is one company that actually is one of the companies that made it super easy for people to use containers. They have the ability to let users create essentially snapshots, so very small packaged applications, standalone applications, or microservice is a very popular term. So for example, if you just want a web server, you can package that into one very tiny, lightweight image, and you can upload it into their cloud. So as you boot up another computer anywhere else, if you want to just take that packaged application and deploy it, you can easily do that. What this means is that you can fully configure your application in one computer and easily deploy it in another computer with the exact same settings. So yeah. So containers allows us to easily relocate existing services. So SAVI IoT, basically, we want to extend this concept of software-defined infrastructure to include the IoT devices close to the users. So essentially, the concept which we're pitching now, infrastructure as code. So basically, we want to empower users to be able to build their own IoT devices close to, and actually be able to leverage our own cloud services, right? And yeah, he has a whole pitch there with bolded terms. So data-sensitive applications, they may have specific requirements for low latency, and that's where the aggregation layer and the edge clouds come in. And if you want to have anything related to restricting the bandwidth of what tenants are doing, doing any sort of quality of service, etc., you can all program this through a central software-defined infrastructure management system. Yeah, I've sort of covered this. SAVI IoT, SDI, SDN. Okay, talked about this a little bit. Right, so like one thing related to IoT nowadays is that a lot of people are again revisiting the idea of a completely fully autonomic system. How many of you here are familiar with IBM's autonomic loop? It's a very famous picture. So basically, you're continuously sensing the environment, and based on the changes you detect, you decide how to react to it, all in a programmatic fashion. So that the whole point is to try and remove as much of the human element as possible in terms of maintaining the application or the infrastructure. So this requires very smart and robust code. This is, again, high-level overview. SAVI, we provide software-defined infrastructure. On top of this physical infrastructure, we can have virtualized resources. And again, on top of this, you can realize a number of different applications. So, yeah, I think that's basically the last slide. So it's not, so any other question right now? Again, he presented his paper earlier this month. A lot of nice stuff. Right now, time permitting, I want to get into the quick hands-on just to give you guys a taste of deploying your own sample IoT application on a platform of virtual machines. And then you'll be able to visualize the resource utilization of these virtual machines as well as the containers and be able to scale it up and down on the fly. So if there's no questions, I'll get into that. Cool. So how many people still have their scripts from this morning? Yeah? Okay, so those of you who want to try this out super quickly, hopefully you still have that. Does anyone who wants one needs one again? Okay, cool. Everyone has one? Great. Slideshow. Use presenter view. Cool. Okay. So here, so as part of this hands-on, we want to do like a multi-tier IoT application platform, and we want to deploy a sample IoT application on there. So again, like the handout, the link to the handout is there for anyone who wants to access it right now. It is the third one. So if you fall behind at any point, just visit that handout. Let me bring it up again. Yeah, okay. So yeah, it's this third one right here, multi-tier IoT applications platform. So if you just click to that, you can see the general outline of this hands-on section. So the first thing that you should do is probably, oh yeah, so do I have it here? Hands-on demo. Okay, yeah, so you will have to, so here, just really quick overview. I already talked about this, so I won't go through this again. So this is essentially what we're trying to realize as part of this hands-on. So we've done, we've set up experiments in the past where we had a small, what we call VCPE, which stands for Virtual Customer Premise Edge. So like I said, a lot of the sensors that you may have at home often are connected via a Raspberry Pi, Arduino, or other smaller type of device. Because of the advances in computing, we can now have these like very small, relatively lightweight devices. I think they're only about like 2 pounds each, 1 or 2 pounds each. And basically they have pretty good computational power. They usually come Wi-Fi and Bluetooth enabled, and you can even attach USBs with any other type of communication protocol that you want, like Zigbee protocol or whatever. So you can have a number of sensors. They can be aggregated via either the Pi devices themselves, or they can be connected to a slightly more powerful customer premise edge. So the good thing about these new devices is that, especially if they're Intel, so that usually means that they support the instruction set architecture to allow you to actually virtualize them, in the sense that you can spawn VMs, you can spawn virtual machines and containers on this thing itself. So this means that you can actually have these basically very lightweight servers connected to the same management platform as the SAVI Testbed. So you can be spawning virtual machines in computers within your own home, as an example. And because like a lot of people nowadays, they don't want their data to leave the premise. They want to be able to control it on their own device. This is a good balance in the sense that the management of the virtual machines is done via like a provider, in this sense, SAVI, but at the same time, you actually control the actual physical device yourself, right? So as part of this hands-on tutorial, we don't have this right here. So we'll be representing the sensors, quote-unquote sensors and actuators and so forth in the actual edge node, right? So for any of you who ever think you will be playing with sensors and virtual customer premise devices, like I said, these things are really cool. Any other questions so far? Cool. So yeah, so like I said, we did a demo before where we streamed data directly to this virtualized customer premise edge. Within this small machine, we were able to boot up two virtual machines. And these virtual machines would aggregate the data, do some pre-processing on them, and it would stream this data upstream to another virtual machine in the edge of SAVI, which would do some more aggregation, more heavier processing. The edge nodes in SAVI often contain heterogeneous devices, in the sense that they have GPUs, they have FPGAs, so if you want to do any high bandwidth, high computational power processing, that's exactly where you want it to. And then it can store the data in like a big heavy duty core data center, where you can have a web server, for example, to visualize the data. So in this tutorial, you'll be creating an IoT platform infrastructure. So basically this platform will be realized using virtual machines across 2 different regions. Unfortunately, I already mentioned we don't have access to a VCP, because like I said, in reality, you would ideally have virtual machines in the core, in the edge, and in these small virtualized customer premise devices, like right in the same room as where the users are. But we'll put the aggregators essentially within the edge for the purposes of this tutorial. And then after that, we'll deploy a sample IoT application. Essentially, this application will be composed of sensors that collect some information, and it transmits it via a messaging system, in this case using Kafka, to an edge processor. These edge processors will just do some basic, simple, it'll read this data, do some basic processing on them, and then it'll send it upstream to the core, where it'll be stored into a database, and this data can be visualized in the web using a web GUI. So let's get started. So if you haven't logged back in already, log in now. If you guys don't remember the OpenPutty or terminal or whatever, the URL for the SAVI client machine is client1.savitestbed.ca, and using the credentials that you have with you. I'll wait for people to log in. if you're logged back in, go ahead and do this source SAVI stuff again, which you did this morning, just to set your environment variables. And again, use the credentials provided on the handout. Project is the tenant name on your sheet. The project is the tenant name on that little strip. The tenant name. So, workshop. That's the project. So, quick show of hands. How many people have got this part? 1, 2, 3, 4, 5. Okay, 6. Cool. Okay, so so basically, within this morning, as you saw, there should be a ComSoc 17 folder within your home directory. And within that directory, now there's another folder called IoT Platform. CD into that. And within that directory, there should be a single shell script. Run that shell script with the region name indicated on your little strip here under session 3. So under session 3, there should be a specific region name on this thing. So just run the IoT init.sh script and then input the region name under session 3 as that. So basically what this script will do is it'll create and upload an SSH key pair. A key pair for you to SSH into a VM, which it will create. And it configures a bunch of security groups, and you'll see that it configures a lot of security groups, like a lot of rules to allow TCP and UDP communications. And finally, after it configures the security group rules, it'll boot a IoT controller VM. So basically, what this IoT controller VM is that it's simply put, it's a virtual machine that contains what's called Docker machine. So basically, from this one VM, you will manage a whole cluster of other VMs. So I pre-configured that virtual machine image with the necessary tools to allow you to remotely manage a group of other virtual machines. So how many people have run this? Or do you have any errors? Sorry. Sorry? The region name? Oh, it's under session 3. Okay. Yeah, let's use that. So I assume people have this done? So for now, just so verify the virtual machine has completely booted up by simply typing novalist. Identify the IP of that virtual machine and SSH into it. So this virtual machine, essentially, I've pre-configured it with all the necessary tools for you to be able to do this part of the tutorial. Yep.
It fails to verify the SSH. And your docs don't have support instructions for that, but it like to allow those.
It should just be .ssh. you may see a certain error when you SSH due to IP conflict. Something about known hosts. Oh yeah, yeah. So yeah, that's exactly the same thing. Just there is so you see. So you see this line here. It says remove with and then this line. Copy and this line. That SSH key can copy that entire line to the very end, and then run. It's the same thing. Yeah. Okay. So it seems like everyone has this issue. You see this line here, remove with, okay, so copy and paste these two here, and then yeah, just paste that. Does anyone else have issues SSHing in because the same issue one?
Yeah.
Oh, okay. That's partially my instructions. Yeah, okay. Let me update this a little bit. Oops, sorry. If you type Novelist and you don't see it, try adding this extra bit in there. So -- OS region name core list. No. If you don't see it,
Okay.
yeah. If you don't see it, try to type it out. Yeah. Good. Cool. Yeah. So after you SSH in, you should see a directory just called IoT. So I would cd into that directory. So cd IoT. Right. Okay. So this machine, this virtual machine that you just created, it contains something called Docker container. As I mentioned, it's a tool for interacting with the cloud. It can work with VirtualBox or it can work with OpenStack systems. And it basically boots up a whole cluster of other virtual machines and then installs Docker within them. Docker is a tool for managing containers. So basically it allows you to manage a whole cluster of virtual machines from a single point and then also manage container services. So before doing this, you need to set your credentials again. I know it's a little bit cumbersome in a configuration file. If you're not, I would save your If you want to, the easiest way to edit a file in Linux is to use Nano. If you're comfortable with Vim, go for that. So type this command to open up that file. Yeah, copy and paste this line. SSH all the way to the SSH copy and paste from there all the way to the end and paste. Can I try that? Yeah. It's in the oh, that's SSH to the first. SSH, yeah, SSH to the end. Yeah. Yeah, copy and paste this line. SSH dash F. It's in the copy and paste that line. From there to the end. So once you've opened that file, you should be presented with a number of placeholders, which I've bolded and colored in yellow. For the username, password, tenant, and network, so basically this field, this field, this field, and this field, use the credentials on your little strip. So some of you were asking this morning, what is the network name for? The network name is for, on your strip is for here. For security group, just type in defaults. And for the edge name, specify again that edge name under session 3. So I'll walk around just to make sure everyone's marked out. So when I say specify default up there, I mean literally replace the XXXXX with the word default. So yeah, because there's not that many people, I'll just run around quickly just to verify everything's okay. We're good? You replace all the So yeah, if you're a little bit behind, again, everything's on that big handout. So how many people have filled this in? All right. So if you don't know how to save and quit in Nano, I included these instructions just in case. Actually, I also included Vim. So like you're using Nano, if you open it in Nano, to save, just press Control-O, and then press Enter. And then to quit, press Control-X. So save and quit. And if you're not using Vim, ignore the stuff at the bottom. I code in Vim all day, so.
That's terrible. I'm sorry to hear that.
I managed an entire testbed, so everything is through SSH. There's no GUI. You pick it up pretty fast when you have to.
Yeah.
It's muscle memory. So everyone's managed to save it? Okay. So now you can deploy the base infrastructure. So basically, what was the point of all that we just did? That basically tells Docker machine where, like which regions of the SAVI testbed to go to create the cluster of virtual machines. So just to recap, so far all we did was we created one virtual machine, which is the IoT controller in SAVI. From that one virtual machine, we're now going to create a cluster of other virtual machines. So if you're not already in the IoT folder, which I think you should be, CD there, but if you're already there, run the platform management.py script, which should be in your current directory, and just what creates us the first arguments. And that should start deploying your infrastructure, which should take about 6 to 8 minutes, hopefully 5 to 6, but I was very conservative. So is everyone there, or? Okay, so at this point, if anyone has problems, let me know. Yep. Errors? Okay, let me check the yeah. So while that's happening, I'll explain what it's actually doing. By the way, if you guys see errors, let me know right away. It's 99% of the time, it's probably something wrong with the input file. So yeah, I'll quickly explain what it's doing while we wait. So basically, this file, it'll create, for this tutorial, it'll create 2 VMs in the core region, and it'll create 2 VMs in the edge region. In the core region, it'll create a swarm master. This swarm master controls the deployment of the IoT containers across the other VMs. In addition, the swarm master is also used to host an ELK stack. For anyone who's played around with big data a little bit, ELK stands for Elasticsearch, Logstash, and Kibana. Elasticsearch is a company that's gotten really good at creating software for data analytics. So basically, the ELK stack will allow you to visualize the data that you'll be collecting. In addition, the script will also install what's called beats, Docker beats, for monitoring the utilization, the resource utilization of both VMs and containers. So you get a very granular monitoring system when you can monitor the per container resource utilization. It'll also create a virtual machine for the database in the core for storing this data. And then it'll create a third virtual machine at the edge region, which hosts what's called edge processors. And basically, they just do some basic processing of incoming data from the aggregator layer. Again, as I mentioned early on, traditionally this aggregator layer may be directly on premise where the users are, but for the purposes of this tutorial, it's a VM at the edge. But yeah, so basically this will be used to host sensors, and the sensors will simply collect some data and then stream it to the edge. So any questions so far? Still? Okay, let me check. Still waiting? Yeah. I think with this many people doing it all at once, it might be stretching the system a little bit. Huh?
Closer to the 8-minute mark.
Yeah. Oh, really? I wasn't really timing. So yeah, so basically, as it's printing out, so I mean, what stage is it on right now? What's the last thing you see?
Deploying ELK on small master.
Oh, you're done? Really? Okay. So for those of you who are done, which I guess right now is one, but you're close. So basically, the output script should give you 3 URLs. And these 3 URLs are visualization dashboards that you can use to visualize the state of your infrastructure. I couldn't copy and paste it into the slides, but you should see something like, oops. Yeah, so like this is a sample output of what you should eventually see, but you should realize there's 3 URLs. One at port 5000, one at port 4040, one at port 5601. If you see those 3 URLs, feel free to open up a browser, copy those 3 URLs into different tabs just to see what they show you. So wait. Push region. Yeah, this part takes a bit of time because it's literally creating a giant swarm of machines and also installing containers at the same time. Yeah, that's good. So basically each of those are VMs. Okay, so you're satisfied.
Seems to have some
So yeah, like if you fall behind, everything's kind of So yeah, is it up-ish? So it's up for you, it's up for you, it's up for you. So you can see all the dashboards? Yeah? Yeah, that, like I said, usually, so like when I'm doing it alone, it takes like 5 to 6 minutes. I guess with everyone doing it, it takes forever. Yeah, you see in this trial run, it only took like, actually, yeah, that's quite a bit of time, yeah. Yeah, so those of you who are behind, I'm just gonna move forward for now. There's the handout that you can always refer back to. So yeah, so try visiting the URLs and then you can play around with it just to explore what those dashboards can show you. So what I want to do right now is I want to create the application. So right now all you've done is create a host of machines and you've installed ELK, and other necessary tools to monitor the resource utilization of your own virtual machines, right? And basically all this data, like the CPU utilization, memory utilization, whatever, all this data is being streamed to a dashboard. And you can see what's going on in one of those 3 dashboards, which we'll configure later on. So basically this platform can be used because this platform is already multi-region. You have VMs in Edge, you have a VM in Core with a database, and you also have a VM in, well, in this case, in the aggregator layer, but like I said, for this, it's in the Edge. You can deploy any sort of multi-tier application that you can envision. So now, like, we'll deploy a very simple IoT app. Within the directory, the IoT folder directory, there should be a script called IoT_app. So just run that with the create parameter. And all this will do is it'll deploy sensor containers in the Edge VMs, and it'll deploy Edge processor containers in the Edge VM. And it'll also create the full data pipeline to connect the data feed from the aggregator to the Edge and to the core database that was booted up earlier. And you can check and verify the status of the application deployment by running IoT_app list. So under the hood of all this, as you've probably heard me mention multiple times, it's a tool called Docker, which is one of the main tools, the most popular tools for managing containers and groups of containers. There's other tools out there as well, and if you start getting into the IoT field and you start playing around with containers, I highly recommend that you guys just explore the ecosystem, because different tools have different strengths and weaknesses. Like Google uses Kubernetes. I know and Kubernetes is their own, I believe it's their own software, if I remember correctly. So everyone run this, and did it finish? Yeah? Good? I see she.
Yeah, we're still waiting.
Really? So what regions are, where one of you
WT1, but we're at now.
Oh, it's up there? How long did that take?
926 seconds.
Okay, so that took 15.
Almost 12.
Pretty nice.
Yeah. I'm confident it'll eventually come up because there's
Yeah, actually ours went to the next level.
Oh, okay.
Before that, so.
Yeah. Yeah. So how's it? Okay. So just make sure so basically the IoT app list, it checks all the containers deployed throughout your system, and as you can see, it's a huge list of containers. Just make sure all the replica ratios are full, like 1:1, 4:4, etc. So now, like, what do you want to do is you want to be able to visualize the health of this huge ecosystem that you just created. So so one of the dashboards, one of the 3 URLs that you pasted in is the Kibana dashboard. So in that one, it's the one with port 5601. On the left-hand side, click on dashboard. And then after that, click on Elastic Scale Monitor. Elastic Scale, okay, that's a typo. And what you should see is like a number of really big graphs. So you'll see a huge number of graphs representing different types of data. What I want you to find is the one graph that says the average CPU utilization per microservice. In this case, when it says microservice, essentially it's talking about a container. So basically the average CPU utilization of a container. And I want you to expand that graph so it's full screen. So everyone expanded it? Or those of you who, cool. So once it's expanded, let's just, for the purposes of the demo, to make it easier to visualize what's going on, let's configure the x-axis really quickly. So on the top right-hand side, click on last 15 minutes, then click on relative, then set the 15 to 5, and then finally just press go to configure the x-axis. No?
Yeah, there's two links were defined, but this one won't load, but we're in Firefox.
5601?
Yeah.
Oh, have you tried Chrome?
Pick up from.
Yeah, try Chrome. I remember someone earlier this morning said it didn't work in Firefox. So if that's done, what you also want to do is you want to make this data auto-refresh by default. I don't know why they implemented it this way. It doesn't auto-refresh. So again, click on the, well, it's not last 15 minutes anymore, it should be 5. 1, click on the thing on the top right-hand side. 2, click auto-refresh. And then 3, change it to 5 seconds, which is their minimum refresh rate. And then you should start seeing the graph update every 5 minutes. Sorry, 5 seconds.
Actually, I don't think that much option in Firefox.
Or best guess.
So how many people were successful with that? So what you should now see, like the line that I want you to pay attention to is the line that says it's a line that says IoT edge processor. This should be in the previous slide, but right. Like observe the average CPU utilization of the edge processor. So like I said, this edge processor is basically responsible for receiving data from the sensors and doing some preliminary calculations with it. So as you can probably imagine, the more data that gets streamed in, its CPU utilization should shoot up, right? So, so let's observe what happens. So now we want to increase the CPU utilization of the edge processor. So we do this by scaling out the sensors. And by scaling out, I mean horizontal scaling. Which, by the way, who here knows the difference between vertical and horizontal scaling? Just to see who knows cloud terminology. So vertical scaling is when you have a single resource and you quote unquote vertically scale it by giving it more resources. Like for example, you give it more memory, you give it more disk space, you give it more CPU time, right? So it's the same resource, you're just giving that one virtual resource more access to the memory, RAM, memory, CPU, etc. Horizontal scaling is where instead of changing that one virtual machine or container, you basically replicate the number of them. So that's horizontal scaling. So in this case, we're going to be doing horizontal scaling in the sense that we take that one we increase its CPU stress by increasing the number of sensors. So basically, we can scale the sensors. So within that IoT folder, you can run scale sensors and then specify a number. So in this case, for the purposes of this demo, let's scale the number of sensors to 10. And wait like 10 to 15 seconds, you should see that the IoT edge processor average CPU utilization should start shooting up. Do a quick walk around. So did everyone see it shoot up? Those in the back? Yeah? So for those who saw it go up, so what do you do when it goes up, right? You want to, so basically now you have a large number of sensors. So that's basically consuming all the CPU resource of the edge processor. So what should you do? You should scale the number of processors. So you can do that right now with scale processors and then specify. That's a typo, that should be processors. So scale processors and then specify a number. So let's scale it to match the number of sensors. So what you realize that we're doing right now, or what I've given you, is that I've provided you scripts to do a lot of this. But in an actual system, like you can create basically a long-running software process that actually monitors this on the fly. Because as you can see, you can continuously monitor the data and you can make autonomic decisions. So you can programmatically create the logic that's required to automatically scale up and down based on usage. And because all this data is actually being stored in a database in the core, you can even do historical trending to learn when these services are actually being used and when they go down. So you can proactively scale, for example, the processors before a lot of people use them. This is just a very, very simple demo, but I hope this at least gives you a taste of how easy it is to make resources elastic using containers. So yeah, so if you haven't already, increase the number of edge processors to 10, and then wait 10 to 15 seconds to see if it shoots down. And again, you can list the number of containers using the IoT app command. Yeah. So right now it's the average is that one average is that all containers. So keep in mind these containers are running within a virtual machine, so it depends on how many virtual CPU cores are established. yeah, something's working. That's good. What about over there? Good? Cool. So yeah, as I said, you should observe the average CPU utilization of edge processor drop in the Kibana graph. And you can feel free to play around with the scaling of the sensors and the edge. Just scale it to however number and see how it reacts. It usually takes about 10 to 15 seconds after you do it for it to be reflected. Yeah. So any questions so far? I know this was a little bit cookie cutter, like step by step. No questions is sometimes a good thing, sometimes it's a worrying thing. Okay. So yeah, so what you can do now, like if you're done all that, you can remove the sample IoT application by running IoT app destroy. That'll basically decommission all the containers that host the sensors as well as the edge processors as well as the Kafka messaging pipeline. So note that destroying the IoT application just removes those things, but it doesn't destroy the platform in itself. So the platform is essentially the set of VMs used to host these containers. So the platform is still there, such that you can easily reuse the platform for hosting any other wide range of IoT applications that you can think of or develop. But if you want to decommission the platform as well, you can simply run the Python platform management.py destroy, which will kill all the VMs essentially, and release those resources back to the pool.
Actually, are these scripts are yours?
Hmm?
Are these scripts are yours?
You asked if they're mine, or? Well, so basically, everything was basically more or less rushed in the last 2.5 weeks. So basically, we had 3 people working on a paper. Their goal was to submit by, I think, 2 weeks from now. So they had disjointed pieces. One person had developed basically a data pipeline with Kafka, Zookeeper, etc. So this data pipeline is basically for streaming data. Another person created a set of systems, like sensors, to feed data into the pipeline, and then a third guy created the visualization system. So their goal was to target for a paper in which they would slowly merge everything together. But then this came up, and I said, okay, we need this sooner than planned. And yeah, the platform management.py was created by, as I mentioned earlier, there's a postdoc in SAVI right now that's responsible for the changing of directions to make it more of an IoT management platform. That was created by him. I heavily modified his code for the purposes of this tutorial, but everything is up available on GitHub. I can show my GitHub really quickly, actually. Where is GitHub? Yeah, I put it in a separate. So my GitHub name, if you're curious, is just oh, you don't see it there. Yeah, my GitHub name is just t-lin right here. As you can see, I forked it from another guy, and I just heavily modified it. I created a new branch within that repo called comsoc, so all my changes are in that one branch on GitHub. So you can see the changes that I made, and etc. And also if you're interested in any of the other scripts we used today, again, it's another repo under my name called comsoc17. So yeah, any other questions based on anything that we did today? If you have any questions, just you're free to email me. You all have access to that master Google Doc handout. I suggest if you're curious, just bookmark it. And yeah, and I think, okay, so we're a little bit early, which is good. It's not a bad thing. Let's see here. Where is? Okay. So yeah, there's no other questions. Yeah, my email is right there. Professor Leon Garcia's email is there. And for general inquiries about SAVI Testbed, just email tb-uot@savinetwork.ca. Yeah. So yeah, cool. So everyone's destroyed their platform management destroyed. If you've done that, great, you're done. You can log out. Is it still waiting?
I think so.
Oh my god.
Like,
Yeah, that's the only thing.
The keyboard takes like a month, and then every keyboard
Yeah.
style like so
I believe that because I'm like, oh, I don't have any of that.
yeah.
But again, that's something that could use to process. So we can learn that. But yeah, it's, I mean, again, we're in the home button.
Calculating on Windows based.
yeah, it's 20.
Oh,
Yeah,
yeah.
that's just like, I'm not sure exactly what the objective is.
I wonder why I wanted to like keep it here. So I can walk over to dogs.
Maybe they just press the button.
See, that's where I'm less
Quite
certain.
for us, and then they got all the pressing power.
Yeah.
And then, yeah.
I could do a lot, but if I just give myself access to a powerful desktop at home and access that for all me, I can do as much. Yeah.
So yeah, with the credentials on these strips, I probably won't shut down the accounts anytime soon. So at least like a week or two. So you're free to play around with it, as long as you don't create any botnets or anything like that, or mine bitcoins.